Jorge Lauret from Universidad Nacional de Córdoba, who's going to speak about homogeneous Ricci flows and solitons.
Thank you very much. Well, thank you very much also to the organizers for the invitation. Feliz cumpleaños, Marcos. Parece de 50. Well, and today I will talk about the Ricci flow, which is already like a subject in its own, and it seems to be worth to study in your favorite framework. I will consider in the homogeneous case. What can we say about the solutions? Is actually not much yet, and most of the talk will be work in progress. We will consider instead of the real Ricci flow, we will consider an equivalent flow, which is from a very algebraic point of view. Yeah, I must warn you that homogeneous implies algebra. Homogeneous Ricci solitons, which are one of the, I don't know, nicest or most interesting concepts which provided by all this Ricci flow story. Is a class of metrics generalizing Einstein metrics. And well, algebraic solitons, and at the end some relations with the Alefsevsky conjecture on Einstein homogeneous manifold. So let's take a homogeneous Riemannian manifold. It's a Riemannian manifold such that the isometric group is a Lie group always. So it is large enough to act transitively on M. That's homogeneous. And then, well, any actually closed Lie subgroup acting transitively on M gives rise to a presentation of the homogeneous manifold as a homogeneous space, a quotient. And so we start with the algebra. K is just the isotropy subgroup. The isometry is fixing the identity. And well, this inner product here will actually determine the whole metric, and is an inner product on add K invariant inner product on P. And recall that P is identified with the tangent space at the identity. So any actually inner product at K invariant on P will give us a homogeneous metric on G over K, a G invariant metric. Okay, so this is so remember always that I mean everything is determined by this like algebraic data. We have then we will have fixed this decomposition of the Lie algebra G of G, and well, the inner product on P. So for instance, any kind of curvature will depend only on this inner product vector space and the structure of Lie algebra, the Lie bracket of G. Any kind of curvature or any geometric quantity actually. Okay, so this is our Riemannian manifold. take then the Ricci tensor will be just a bilinear symmetric form on P, and we will denote in this way the Ricci operator, which is just to see the Ricci tensor as a symmetric operator instead of a symmetric form. That's the Ricci operator. And well, consider the Ricci flow starting at the metric G, which we have identified with this data. This is the Ricci flow, is to evolve the metric in the direction of the Ricci tensor. And a very good thing in the homogeneous case is that it's a general property that isometries are preserved along the flow. So that follows very easily from the uniqueness of the solution, that any isometry at the starting metric will be an isometry for all t. And then for us, that's very useful because we have then the whole G, that connected Lie subgroup of the isometric group acting transitively fixed for all t. And then we can have our algebraic data fixed, except the inner product. So we will have the quotient, the homogeneous space, as a differentiable manifold fixed, and the composition also fixed. And then the only data which will evolve will be the inner product, which for all t will be an Adka invariant inner product on P. Okay, so the Ricci flow, of course, will be in this case, since we are only in one of the tangent spaces, fixed, then it will be an ODE instead of a PDE. This is the ODE then for Ricci flow. And if we fix the starting metric, then we can write the Ricci flow for a curve of operators on P. This H of T, of course, is not unique. You can put any orthogonal transformation here and you will have the same. So, and we will see that, well, choosing that H will be, I mean, different H's will give us, I don't know, more nice ODEs, nice equations. So it's important to choose that H correctly. For any H, the ODE, the Ricci flow for H, is this. Is not very nice, and well, but remember then that the Ricci flow will be described in terms of a invertible linear operator of P. Okay, so we have then this Ricci flow. We have the decomposition of the Lie algebra of G fixed, and then it's like we can, I don't know, use the following trick, which is to see how the Lie bracket evolves. I mean, instead of fixing the homogeneous space and moving the metric, it's like we could fix the metric and evolve the homogeneous space. Why is this? I don't know. Why do we do that? One reason is that the convergence questions are very important, and I mean, for all t, we have like the homogeneous space is fixed. But in the limit, if you get the limit by scaling for some function, it's like you might obtain another homogeneous space, and even with another topology, with a different topology, and then it's like it's very difficult to see the limit if you evolve the metric, and this point of view sometimes at least helps you to see what is the limit. The homogeneous spaces will be converging to that limit you want to know. Okay, so it's just take the h of t on P and this identity on K, and then you have a linear operator on G, and you have the bracket on G, and well, define this curve of Lie brackets. It's a curve of Lie brackets on G. They are all isomorphic to the starting point, because by definition, right? This is like a change of basis. And so, well, h of t defines this curve of Lie bracket. Assume G is simply connected. Since M is connected, then K is connected. And then it's like we have a curve of homogeneous spaces, homogeneous Riemannian spaces, determined for all t only by this this curve at time t, curve of Lie brackets. So a natural question, well, what is GT is the corresponding simply connected Lie group with this new Lie algebra, which has the same underlying vector space but a different bracket. GT is isomorphic to G for all t, but this another one. It's a different Lie group, if you. Okay, and the decomposition as vector spaces is the same, and well, is actually for all t isometric to our Ricci flow. So it's like a, I mean, it's like it's similar to the Targ's flow. It's called that. It's like you have the Ricci flow and change. You take another flow, another curve of metrics, which are isometric for all t, but maybe your new flow, I mean, is easier to study, is more friendly, and well, that's the trick. In this case, then, this is the trick we propose to evolve the homogeneous spaces, to evolve the Lie bracket instead of the inner product, and to see what happens, what would be the Ricci flow for this curve of Lie brackets. Okay. So first result is that if you take the Ricci flow and take this H, this is as I said, this is a very special H. Is the H solving this ODE for a linear map. Then you have, I mean, you don't have to assume that this H is the Ricci flow. It's a consequence that the Ricci flow is given by this H, and the corresponding Lie bracket satisfies the following ODE. This delta is just something which is measuring, well, first this Ricci is of course the Ricci operator of the corresponding homogeneous space, homogeneous Riemannian space corresponding to this Lie bracket. Remember, we have fixed an inner product, so any of these Lie brackets gives us a homogeneous Riemannian space. which is this one, denoted by this. And this delta is just the function measuring how far is the operator A from being a derivation of the Lie algebra. Okay. So, then for this special H, we have this more or less nice ODE for the Lie bracket. This one. Okay, this delta okay, is 0 if and only if A is a derivation of the Lie algebra. This trick, this ODE, has been used by Galina Guzbina in her thesis to study the Ricci flow for nil manifolds, which are left invariant metrics on nilpotent Lie groups. We will back to these nil manifolds at the end of the talk. Okay, well, to make the things even more algebraic, let them concentrate on this, focus on this bracket flow. So fix, this will be very abstract and well, it's not a bad idea to when one studies these homogeneous spaces to really, I mean, really separate the real important algebra information to get results. So fix G with this inner product as only as an inner product vector space for now. So we will be moving the Lie bracket. So let's consider only as an inner product vector space and take an orthogonal decomposition only as a vector space. Orthogonal means always with respect to this fixed inner product we have, and let's denote by mu a bracket. It's an element of this much bigger vector space, the vector space of all bilinear and skew symmetric forms on G. And if one checks the definition, as I said at the beginning, of the Ricci curvature, of the Ricci operator, one can see that everything depends, I mean, the definition doesn't use the Jacobi identity or many of the properties you have when you have a homogeneous space. It's like you can define in an abstract way the Ricci operator only having this inner product on P, and for any mu of this, which I mean in principle it doesn't have any geometric meaning, but you can define it. Let me define more precisely the Ricci operator in a homogeneous space later, but it depends on three parts. This is the Killing form, this is measuring how far are you from a unimodular Lie algebra, and this is, well, the moment map for certain action. Okay, so for a curve of brackets, we can consider the flow we had in the lemma. And so when one of these mu actually gives us a homogeneous Riemannian space, is you need these properties, these conditions. Of course, mu has to be a Lie algebra, so Jacobi, Kk is in K, Kp is in P, and well, this already gives us simply connected group G mu, and K mu, the corresponding connected subgroup with Lie algebra K. Recall that K is a Lie subalgebra. You need K mu close in G mu in order to have a differentiable manifold, a differentiable structure. And, well, you need that the inner product be, oops. It's not mine. I'm from Argentina, but I didn't. Okay, then this is, we need also that this inner product be invariant. This means that all these adjoint operators be skew-symmetric, and so this implies that that is K invariant for the group because it's connected. And we need this, which is called this implies almost effective, the action almost effective. And so this is more or less that, well, no, it doesn't matter. Okay, this is, with this four condition is enough to have that, I mean, to have that mu actually correspond to a homogeneous Riemannian space. But the good thing is that these conditions are preserved by the bracket flow. So if you start with a homogeneous Riemannian space, then you will have a homogeneous Riemannian space for all T, and then you can study this abstract flow and well, you will get a curve of homogeneous space, and also that is precisely the equivalent to the Ricci flow. Okay, then take then one homogeneous Riemannian space and take this abstract flow, the bracket flow, and the thing is that if you take H now to satisfy this ODE, then well, mu of T is actually the curve of Lie bracket is in the first lemma, and this is the Ricci flow on M with this Riemannian manifold as starting metric. So it's like we have an if and only if, an equivalence, very specific, and since we have this property for all T, these curves are the same in both lemmas. So let me give a summary. I mean, for those which are really lost, let's start again. Let's take then a homogeneous manifold, homogeneous Riemannian manifold, a presentation as a homogeneous Riemannian space. We have the Ricci flow, which is just a curve of inner products on one of the tangent spaces. It's an ODE. And then what I have said up to now is just that it's equivalent in a very specific way to a bracket flow. This is a very different flow. It's a different vector space and a different equation, but it's equivalent in the sense that to go to in any direction, you have to solve that just to solve this ODE for H, and then you go from one to the other in this way. Okay, then we can study the bracket flow and get results for the Ricci flow. For instance, since this equivalence, the question of what is the maximal interval of existence is the same. It's the same, and since they are all isometric for all T, at each T they are isometric, then the geometric quantities, I know the norm of the curvature tensor, the norm of the Ricci, any invariant, Riemannian invariant is the same for all T, and the problem is the convergence. This is not, I mean, even if you have equivalent flows, it's like one of them could converge very clearly to some Riemannian manifold, and the other you can't see. So that's still, I don't know, a mystery. I mean, if you get a limit from this point of view, how to translate, but okay, well, it's Gromov, Hausdorff, and so, but okay, so this is not equivalent. You have to work about it. Okay, then we have this homogeneous space, fix this decomposition, take the solution to this bracket flow. Remember that delta measure how far is this from being a derivation of the algebra mu. A first result is that this bracket doesn't move on K or the action on K on P. So it doesn't, so this is constant on time along the flow, and so the only two parts of mu of the Lie bracket on G which really moves are these, P times P on K and P times P on P. This part is the most, I mean, important in Riemannian geometry, because it's the part which most appear in the formulas for curvature. Okay, it's the Lie bracket of G, is restricted and projected on P. So the bracket flow is this flow for mu K, which is the projection on K, and this flow for mu P. Okay. Let me describe the Ricci operator for a homogeneous manifold. Is so three parts. B mu is the Killing form. H mu, as I said, is zero if and only if your Lie algebra is unimodular, which is that this trace is zero for all x. And the third part, this R, is defined like this, and then is precisely the moment map for this, the natural linear action we have here, the change of basis action we have of GLP on the bilinear skew-symmetric forms on P. What's the moment map? Well, it's something very natural to define for a representation. The name comes from symplectic geometry, but to study linear action is a very natural. I mean, you can have even here odd dimensions, so nothing to do with symplectic geometry, but well, it uses, of course, the ideas and the philosophy of symplectic Hamiltonian actions. Okay, one remark is that only the Killing form depends on all the Lie algebra G. On mu, these are operators on G, the whole G. R and H depends only on mu P. Okay, I have some, it's easy to compute some ODEs. Remember that you have this delta measuring how far is A from being a derivation, and define this delta as delta transpose respect to the natural linear products. This is actually the Laplacian for the Chevalley cohomology. The Chevalley cohomology is a cohomology of Lie algebra with values in the adjoint representation. And at level 1 or 2, this is precisely the Laplacian, which will be involved in the ODE that R satisfies. So this R, which is the moment map part of the Ricci operator, satisfies this ODE. with this Laplacian of Ricci. For instance, the Killing form satisfies this kind of, how do you call, Riccati equation. This is the equation for H, and well, this is the equation for the scalar curvature, which is actually the general. Remember that in a homogeneous spaces, the scalar curvature is just a number. It's not a function. So the scalar curvature increases along the flow. This is for the square norm of the Lie bracket mu p. And this H satisfies this ODE, so it's like the flow is taking you to unimodular things in some sense. Okay. For instance, so all this I'm actually trying to find more applications. Up to now, we have applications to the case of nil manifolds, which are nilpotently groups with left invariant metric. So as homogeneous spaces is G nilpotent, K is just the identity, so P is equal to G. And since for nilpotently algebras the Killing form is 0 and they are unimodular, the Ricci operator coincides with the moment map, which is actually the key of all these results. Because, well, the scalar curvature, for instance, is just minus the square norm of the Lie bracket. And this is the bracket flow. And the first very good thing is that it's a gradient flow in this case. In this case for any nil manifold. Because this is precisely the minus the gradient of this functional, the square norm of the Ricci tensor. And it's not only a gradient flow, it is actually this famous gradient flow, which is the negative gradient flow of the square norm of the moment map, which has been studied a lot from not only in symplectic geometry, also from geometric invariant theory. And then we can use all these results or ideas, actually. Because now I will prove something, for instance, that, well, it's like all this relationship with these very important things are hidden. So, but this is really the reason why it's useful in this case. This is a general definition. A Ricci flow is, is called a type 3 solution if it, first of all, if it is defined for all t, it doesn't have a finite time singularity, and the norm of this is the curvature tensor, the Riemannian tensor. So the norm of the Riemannian tensor is bounded for a function like this. So this is one of the types of singularities that you can have in the Ricci flow. Actually, this is one of the, I don't know, is maybe the worst that can happen to you, because, I mean, if you are looking for a limit up to scaling, it's like, well, if you have this, it's not very good news. Okay, but then let's then consider the flow for the ODE for the norm of the Lie bracket. Okay, so we have this flow for the Lie bracket mu. Remember that bracket flow is completely equivalent to the Ricci flow. And so to see, as I said, to see that this type 3 or not, remember, we can see that on the bracket flow directly. So let's do that. The derivative of the square norm of mu, remember that this is just a multiple of the scalar curvature, satisfy this ODE. We gave the formula for the general case. This is just Cauchy-Schwarz. And this is equal to this, to the norm to the fourth. And then you have that the square norm of the bracket will be controlled by this quantity here, so this is very good news. So it first of all goes to 0, and then it's defined for all t, no problem. It stays in a compact subset. And about the norm of the curvature Riemannian tensor, we just do this. This is very simple. And this C will be the maximum of this function. Remember that this is defined for all lambda in this vector space, like an abstract object, and is continuous because all polynomials. So it will have a maximum on the sphere. And then it doesn't depend on the starting point. So we get that for any simply connected nilpotent group and any G left invariant metric, the Ricci flow will be a type 3 solution. And moreover, that the constant C controlling the norm of the curvature, it doesn't depend on n, well, I have two n's. On the nilpotent group, depends only on the dimension. Because this maximum it depends only on the dimension of G. Okay. So this is one application. And now I'd like to talk about Ricci solitons. So the definition is very nice. One can ask what are the fixed points of the Ricci flow. Then for a fixed point you have this 0, then they must be Ricci flat. But then to get more metrics, you can ask actually for fixed points in the moduli space of metrics. So which are the metrics which are not fixed points of the flow, but for all t are isometric to the starting point, okay? Isometric up to a multiple, homothetic. So the metrics which the Ricci flow cannot improve. The metrics, these are the metrics, I mean, the Ricci flow is supposed to improve the metrics. So these are the metric which says, well, I'm already nice enough. The Ricci flow it doesn't change me. So the definition then, take a complete Riemannian manifold, a Ricci soliton, as you see, is a generalization of Einstein metric. When this is 0, you have an Einstein metric. This is defined for any, not only compact manifolds, for complete Riemannian manifold. So the definition is that the Ricci tensor, well, is not a multiple of the metric, but almost. Plus, this is the Lie derivative of the metric with respect to some field, some complete vector field. Is equivalent to say that the Ricci tensor is not a multiple, it's not tangent to the multiple, positive multiple of the metric, but is tangent to this orbit, to this. These are precisely the set of all metric which are isometric up to a multiple to G. in the space of all Riemannian metrics of M. And is if and only if, what's the relation with the Ricci flow? Is if and only if the Ricci flow starting at the metric G has this form. And it has to be actually with this multiple. So is a 5 of T is a diffeomorphism, so these are all metrics which are isometric to G up to a multiple then. Okay, so this is a Ricci soliton. In general definition is called expanding when this C is negative, steady when it's zero, and shrinking when this is positive, and gradient when this X, field X, is actually the gradient field of a function. And in that case, the formula for Ricci, for soliton, is with the Hessian of F. Okay. Okay, in the case of homogeneous manifolds, we have that this is very, well, I'd like to show this, for instance. This is a result by Lauret. He starts with in a very general case. I mean, just three-dimensional compact manifold M with some conditions on the curvature. He proved that you really get, at least on the simply connected cover, you are converging, you approaches a homogeneous expanding Ricci soliton. So it's like, this is showing that not only these Ricci solitons are like attractors of the Ricci flow, but only the homogeneous metrics are, under some condition, attractors of the Ricci flow. By results of Ivy, Naber, Perelman, and Peterson-Wiley, one can show that any non-trivial or any non-Einstein homogeneous Ricci soliton must be non-compact, expanding, and non-gradient. So it's very restrictive. To have a non-Einstein Ricci soliton, you have these necessary conditions. Which are the examples we know up to now? They are all very algebraic. Take a homogeneous Riemannian space with G simply connected, and take, as always, a fixed Adka invariant decomposition. This is then an inner product on P. Remember, P is the tangent space of this manifold. Let's give this definition. This homogeneous space is called an algebraic soliton if, for some derivation of G satisfying which leaves K invariant and some constant C, we have that the Ricci operator, remember that the Ricci operator is an endomorphism of P, is a multiple of the identity plus this derivation restricted to P. So it's Einstein if and only if D is 0. So Einstein homogeneous metrics are algebraic solitons. This is the definition, and let me give this very easy actually result that a homogeneous Riemannian manifold which can be presented as an algebraic soliton like this is actually a Ricci soliton. And this is the proof, sorry, but this is very short. We have the Ricci operator, then a multiple of the identity plus a derivation, but this derivation will give us everything. I mean, you can have, since it's a derivation, e to the TD is an automorphism of the Lie algebra. Since G is simply connected, this gives us an automorphism of the group, which actually gives us a diffeomorphism of M by the properties that this satisfies. And, well, the field will be the corresponding field to this one parameter group of diffeomorphisms. This is called a linear field because it's generalized in Rn, the fields given by a linear map with a matrix. Recall that the identity, since these are all automorphisms, they fix the identity, so it's zero, this field. It's a very special field, and it's easy to see that actually the Ricci tensor is a multiple of the metric plus the Lie derivative with respect to this field. So it's a Ricci soliton. An algebraic soliton is a Ricci soliton. Well, normalized flows. One normalizes the flow when one wants limits. Take start with the homogeneous Riemannian space, take any geometric scalar invariant R, and then the normalized flow, this would be a normalized flow. Is the Ricci flow plus something from the metric. And that something is something which is a Riemannian invariant, okay? And for instance, in the compact case, if you put here a multiple of the total scalar curvature, you get that the volume will be the same for all T. In our homogeneous case, we don't need compact because, I mean, we have just a number. And then, for instance, we can put here the square norm of the Ricci tensor, and you get that the scalar curvature will be constant. So it's equivalent to multiply the solution for some scaling function depending on T. By the same argument we did at the beginning, this normalized Ricci flow will be equivalent to something like this, with the R is here, R mu, and then assume that for some normalization you get the limit. You have this abstract flow. Assume that for some normalization you get that mu converges to some lambda. But then mu prime goes to 0. And then delta lambda of this is 0, and that's precisely an algebraic soliton. Because remember that this is 0 if and only if this is a derivation of the Lie algebra. So for lambda, you are getting this 0, so you are getting that the Ricci operator of lambda plus a multiple of the identity is a derivation. That's our definition of an algebraic soliton. So the algebraic solitons are like necessarily the limits of any normalization. I mean, if you find, for instance, in an nilpotent case, you can just normalize by the norm, by the scalar curvature. To get the scalar curvature constant is the same that to stay in the sphere for the flow. And then in the limit, you get an algebraic soliton, which is called a nil soliton in the nilpotent case. But the problem is when you get this, how to translate to the real Ricci flow? Well, that's another question. Okay, so algebraic solitons are I mean, metrics which are really worth to study. All known example up to now of a Ricci soliton homogeneous is an algebraic soliton. The examples are well, when G is nilpotent, these are called nil solitons. And well, we have been studying this nil soliton for many years. they are like in one-to-one corresponding with Einstein solved manifolds. We have uniqueness in the sense that a given nilpotently group can admit at most one nil soliton up to isometry. Thus, well, this is saying you that it's a problem on the nilpotently algebra. It's like a problem on nilpotently algebras. A nilpotently algebra has or has not one of these metrics, but if it has one, it's unique. So it's a property of the Lie algebra. They are precisely the critical points of the square norm of the moment map. This gives us a very nice result from geometric invariant theory to apply and to describe the nil solitons. But, well, we have many questions. We don't have a classification. It seems to be like a wild problem to classify them. We don't know the algebraic structure, and the worst part is that we don't know existent results. Something, I mean, any nilpotently algebra such that, I don't know, some algebraic condition which gives you the existence of a nil soliton. We have some results, but it's like we are far from completely satisfactory answers. Okay, these people found algebraic soliton for G solvable in dimension 3 and 4, and for G solvable we can call them sol solitons, and it turns out that they are like I mean, sol solitons are like not in one-to-one correspondent, but it depends on nil solitons. A general construction which gives all the possible sol solitons is, you have to really, I mean, this is the real problem you have, the nil soliton. The sol solitons is not the problem. It's just to find an abelian algebra of derivation, and that's it. But you have to understand nil solitons to understand sol solitons. They are all simply connected, and we also have uniqueness for sol solitons and, well, classification up to dimension 4. So the open questions in this topic are that we don't know if any homogeneous Ricci soliton will be an algebraic soliton. Maybe yes, maybe not. And we don't have any example of an algebraic soliton which is not a sol soliton. So up to now, all examples we have are sol solitons. And so this is another open question. Well, this is, I don't have time, this is very technical. Some structural result, sorry, I will. Structural result I've been working on algebraic solitons, but the important thing is that the relation with the Alefsky conjecture. We have this long-standing conjecture, it's in Bess's book, which says that any Einstein-connected homogeneous Riemannian manifold of negative scalar curvature is diffeomorphic to a Euclidean space. In particular, it's simply connected. So this is the conjecture, and it is wide open. It is only known to be true for dimension less or equal than 5, but the proof of this result follows from a complete classification. So it's like there are no techniques to imitate there, and it follows from result by Heber and mine that solved manifolds in particular, they satisfy the Alefsky conjecture, and more in general solved solitons. So any soliton is actually diffeomorphic to the Euclidean space. This follows because we know the structure of the solvable groups, and we know that they don't have centers, and then you don't have quotients, which are not simply connected to get examples. But well, this conjecture is like some people think that it is too optimistic because some pessimistic people, Doty and Leite, found in the 80s metrics on SLNR, left invariant metric with negative Ricci curvature. This is why was quite surprising. So metrics, left invariant metrics with negative Ricci curvature. So, and remember that this, I don't know, as a topological space is something like this. So it's not diffeomorphic to Euclidean space. So if one can perturb these metrics to get really Einstein, the same negative constant for all, you will get a counterexample to a Lefschetski conjecture. But well, it's open. Even for SL3, it's not easy to. I mean, it's negative, but the different eigenvalues are very different. Are far from being a multiple of the identity. Okay. And well, it follows from these structural results I didn't show that any example of an algebraic soliton which is not a soliton would give rise to a counterexample to the Lefschetski conjecture. So it's like to find an algebraic soliton which is not a soliton is as far as complicated than to find a counterexample to a Lefschetski conjecture. So it could be true, I don't know. It's like very early in the morning I think it's true, but every day. But then in the afternoon. Okay, just to finish, let me dedicate this talk to the memory of my grandfather, Alfonso Lauret.
Any questions? Comments? Well, if not, let's thank Jorge again.